coming, especially those coming for the second talk. So today I'll be talking about permutation checks. I'll explain what they are. And in particular, I'll be telling you about sort of our newest work called linear time permutation checks. There's an asterisk. We'll get into the details of that asterisk. This is joint work with Jessica Chen and Zach Stefano, who are both PhD students at NYU. So what is a permutation check? So a permutation check, at the end, in essence, there's going to be multiple variants of them, but it's going to be a statement of the two following flavors. Let's say I have two vectors f and g, each containing n elements over a finite field, and I want to prove that they're permutations of each other. So an example, we have 77, we have this vector and this vector, and then these vectors are permutations of each other. And in general, what I'm going to do is I'm going to arithmetize f and g in some way, usually using a polynomial, for example, a multilinear polynomial. So I'm going to define f by saying that f at a certain set of evaluations is equal to these values. So in that way, we can reformulate the problem to say that f and g are permutations of each other if there exists a map, sigma, which maps from the so-called Boolean hypercube, 0, 1 to the log n. So these are strings of size log n, or you can think of it as a mu linear, or as a polynomial from 0, 1 to the log n to 0, 1 to the log n, such that f of x is equal to g of s, sigma of x. Okay. So and yeah, we can even write down what sigma is, right? Sigma of 0, 0, 0, 1. So yeah, in this example. So the main permutation check Don, go ahead, sorry.
Oh, sorry. I actually, it was a technical thing. I got an answer in chat. I'm not seeing the slides, but they suggested to rejoin the Zoom. I'll try again. I see them behind your head, but I'll rejoin and see if that works. I got answers 2 ways at the same time. I didn't know if other people could see the slides.
Yes, it works. Sometimes you can change yourself what you see.
Yeah, I'll give it a shot. So continue. Sorry for the interruption. I got the chat.
Sounds good. So the main permutation check that we're going to look at is one where the permutation is actually so-called pre-processed or indexed. So there's a fixed sigma such that f of y is equal to g of sigma of y. So in this case, fg and some function of sigma, we'll talk about exactly what that function of sigma looks like, are going to be pre-computed and committed. Okay. There's also other variants. So for example, there's the prover-provided permutation check where sigma is not pre-processed and the prover proves that it knows a permutation between f. These have different applications. But we will focus on the given problem generally today, but it turns out that the same techniques with some additions apply to both settings. So why do we care about permutation checks? So it turns out they're at the heart of proof systems. So as an example, we can look at something like HyperPlonk, where I generally encode my computation as a circuit, let's say as an arithmetic circuit. And I want to prove that there's a number of gates in the circuit. And I want to prove that all of these circuits, that this entire circuit is satisfied. So the prover wants to prove that given some public inputs x, it knows some private inputs w, such that the circuit evaluates to 0 or some fixed value. So the way that I'm going to do that is I'm going to compile the circuit to a trace and then encode the trace as a multivariate polynomial, and then prove that the trace encodes a valid circuit computation by proving that a number of circuit constraints hold. And this last step basically breaks down into 2 different checks. So one is called the gate identity check, where I'm basically going to prove that every single gate is satisfied. So every single addition and multiplication gate is satisfied. And then the other one is the one that we will actually mainly care about today. It's the wiring entity check, which you can see here. This, can you see my mouse? Yeah. You can see here that this wire serves two functions. It's both the output of gate 1 and it is the right input of gate 2. Right? And for a circuit to have structure and meaning, there needs to be some sort of wiring structure. So the way that I'm going to do this, or we'll see this in the detail, but this is basically the wiring identity check, which basically shows the consistency between the output of gate 1 and the input of gate 2.
I have a question.
Yeah.
Can you explain how permutation checks fit into the?
Yeah, we will get there.
Oh, okay. Sorry.
Don't worry. So let's say, here's an example. So I have some inputs, 5, 6, and 1, and then I have all the wires. So I compile this to a trace. So I literally write down for every gate, left input, right input, output. I also have the inputs here. And the way in HyperPlonk, and there's different proof systems, but all of them, at the end, they all have the same, they will all look somewhat similar, and they will use either a permutation check or a variant thereof. I'm just gonna give you the example of HyperPlonk, but this is much more general.
So a question. So here the tree doesn't include the circuit itself and the equivalent value.
Yeah, so by the trace, I mean the runtime values. So the trace is the runtime. So this is the so-called witness. The witness is going to be the runtime. Value, or more specifically, we're going to say it's the left inputs, the right inputs, and the outputs. And then the two things that I need to prove is basically, for example, here I'm proving 5, 6, 1. This doesn't even make sense. Oh, this should be 5, 6, 11. Okay. So the output of 5 plus 6 is equal to 11 here. Oh, no, sorry, this is, 5 plus 6 is equal to 11, or 11 times 7 is 77. We're not going to focus on that check. What we're going to focus on is this wiring identity check, right? Where I'm going to have to prove that, these values are going to be the same. And all the slots in this same color should have the identical values. And it turns out that I can write this using a permutation check. And the way that I write this as a permutation check is that basically I'm going to look at all the cycles. So I'm going to say, okay, I'm going to look at all of the values they're the same. So that's a cycle. So for example, 0, 0, 0, 1, 1, 0 is going to form a cycle. And then a permutation is just a list of cycles. So in giving a list of cycles, and that uniquely defines. So the permutation is going to be a mapping that is preprocessed and committed such that f of x is going to be equal to f of sigma of x. Yeah. So for example, here the map sigma would, for example, for 0, 0, it would map to 0, 1. And then for 0, 1, it would map to 0, 0. That's one cycle. Or for the right values, like right 0, 0, it would map to right 0, 1, which would map to left 1, 0, which would map to right 0, 0 again, right? So I'm building a cycle here. And I actually know what the cycle is before I know the assignment of the variables, right? It just depends on the structure of the circuit. It doesn't depend on the assignments of them. Okay, so this is where does that make? Yeah. So how do we do this permutation check? Well, in HyperPlonk, this was some complex, multi-step thing. So, we reduced the permutation check to called a multi-step check, and we call a product check, which then reduces to a zero check, which in the end is proven using a sum check. So it had this whole machinery. And what we're going to do is basically we're going to skip a bunch of steps, and we're going to arguably do something simpler and directly prove a permutation check. And this has both. We'll see that this has both efficiency and soundness, because these steps have some downsides. Okay, it turns out that so permutation check is used for checking the correctness of wiring. They also have other applications. They use in memory checking to prove that all the reads and the writes. So like, let's say I want to prove a machine computation. So this was for circuits. But sometimes, some of the examples I gave in the earlier talk were more related to machine computations, where I read and write from memory. And I have to prove that all the reads and writes are consistent. This essentially, this was invented in 1991, I think, by Manuel Bloom and others. I don't know if he was already here, but certainly one of the CMU greats. And yeah, you basically have to do a permutation check here. I'm not going to go into the details of how this happens, but trust me, sort of also comes up there. The other protocol is, there's a kind of sometimes you have shuffle protocols. I think Elena's worked on non-interactive routing. You sometimes have to, these shuffling protocols where, for example, in network communication, this comes up where, I want to sort of anonymize the communication. So what we do is, I encrypt a bunch of inputs, and then someone decrypts, one layer of these inputs and shuffles them, and then outputs them again, and it has to prove that they did the shuffling correctly. And you can also do this using a permutation argument by just proving that you know a permutation. Mixed nets, exactly. These things are called mixed nets. And then finally, they're also related to so-called lookup arguments. So permutation argument kind of had this flavor. In fact, actually, oftentimes in permutation argument, F and G are the same. In a lookup argument, we're going to write this in this slightly more general form. Because in a lookup argument, G encodes a table. So for example, a table of preprocessed values. So for example, this could be, let's say I want to prove that my value is between 0 and 1 million, and want to do a range group. This has, there's also a bunch of applications in these proof systems. If I want to do arithmetic, let's say over mod 2 to the 32 instead of over some large finite field, then I might have to do some range groups. Or I can even in this table, this has been, I can encode a computation even in a table. So I can write this in a very similar manner where G basically encodes the table, and tau basically says that tau of X says so I want to prove that all of the values in F are inside this table. And the way that I do it is that basically I write down, F of 0, like the first value of F, so X equals 0, 0. Let's say it's the third value in the table, then I would encode that in tau. And I basically encode the indexes in tau and prove that this relation holds. So it's another nested function.
This permutation check can using lookup. I was wondering if you replace this permutation check with the memory checking in the lookups.
No, I'm saying that lookups look like a permutation check.
Yeah, but
So they're not quite a permutation check. No, this is a lookup argument.
Yeah, I see. But yeah, I'm curious how is the permutation check?
So it's not a permutation check.
Okay.
I'm saying it actually has, what we'll show you is that sort of the lookup argument has a very similar structure to a permutation argument. And in fact, the same techniques that we use to prove permutation arguments are going to be useful to prove the lookup arguments directly.
Yeah.
So you don't need memory checking anymore to prove lookup arguments.
I guess the memory checking is still below for permutation check.
What?
The memory checking is also like the interlogram product.
Yeah, memory checking also uses permutation checks.
Yeah, so can we just replace the memory check, the permutation check or the memory checking?
Yeah, we could do that, but first of all, there's some soundness downsides. So it's much better to do it direct, right? What I'm saying is like, yes, of course, we can, do this whole recipe of like You can prove lookup arguments using memory checking, which uses permutation arguments.
Yeah.
And you could replace that little component. But what actually turns out, in some settings, it's very nuanced, but at least in some settings, let's just skip the whole thing and just directly solve the problem. Right? Let's not go through the complications, memory checking, but we can actually directly address the problem. Does that make sense?
Yeah.
But yeah, so permutation checks, they're not the same, but they're highly related to lookup arguments. And yeah, they have a lot of applications in machine computation as well. Okay. So that's it for motivation for now. Are there any other questions for, why we care about these things before we dive into solutions? Don, can you see the slides now?
I sure can. Yes,
Okay.
thanks. Very clear so far.
Good. Okay, so let's see how they're constructed. And you already mentioned something before, that the most common way is to reduce the permutation check to a so-called product check. So if I want to, okay, if I want to prove that this, if I want to prove that two lists are permutations of each other, what I can do is I can just find, like I want to prove that two sets of permutations, or the two multi-sets. What I can do is I can interpolate a polynomial that has roots at the values in the set. Okay, so for example, x minus, let's call the set, A and B. So product of yeah. Where is the train?
Very excited about the polynomials.
Yeah. So the product of x minus ai and the product of x minus bi are going to be the same if and only if ai and bi are the same as sets, right? So whereas listed if they're permutations. Is that clear? And it turns out that even for you can do minus or plus, that doesn't actually really matter. And if I want to, for a specific permutation, I want to prove this, then I can almost do the same thing. I basically add a plus y times x in one side, and then plus y times sigma of x on the other side. And then it turns out that you're proving that these are specific permutations of. Okay, and the way that this is generally done is I can equivalently divide these two sides by each other. Yes, you need to worry about things not being zero, but that with high probability works out, and you prove that this divisor, this product of this divisor is equal to. So, question, assume these lists are not the same. So what I want to do then is I want to test this essentially at a random point, y, capital Y and X. Let's forget about the Y part for a second. Let's just worry about the X part. What is the probability? Let's say f of x and g of x are not the same. What's the probability that they're going to be the same at a random point X?
2 to the mu divided by the probability.
2 to the mu divided by the set of the randomness, yeah, by the size. And usually I draw the randomness from the size of the field. So yeah, so it's going to be 2 to the mu is literally the number of elements in F and in G. We call that n as well. So it's n over the size of the field. So the soundness error is n over the size of the field. The other thing is, what I do is to prove this, I need to do something called a product check. So I'm going to commit to all of these little terms, right? All of these, or actually what I'm going to do is I'm going to commit to so-called partial products. So that's basically the product of these, in the end, I'm going to do a product over n things. but I'm going to commit to the product over 2 things, over 3 things, over 4 things. And then I do some, you don't need to worry about the details here. I do some consistency check between these 2. So what this means is that I actually need to commit, in order to do this product check, I need to commit to n additional elements. And in fact, one thing that's interesting is that so it has soundness error n over the size of field. The other thing is that even if the elements in F, they might be small elements. They could be bits, for example. Even still, this product or this fraction here is going to be large. Partially because I'm using large challenges for R1 and R2, but also because it's the product of multiple things. So these products are these challenges are these partial products are large bits. So committing to them is expensive and wasteful, and in particular, sort of to sort of go back to. Yeah, actually, we'll talk about that in a second. So and I need lambda. So it's going to be 256 under the discrete log assumption and 120 in the 120 in the it's going to be 120 in the in hash-based systems. So why do I care so much about this commitment being wasteful? Well, it turns out that in the SNARK application, if we go all the way back to the main thing, the main proof of work the main thing that dominates the proof of work is committing to F, committing to the witness. So if the witness is small, right, generally the commitment cost is linear, not just in the number of elements in the witness, but also in the weight of the witness. Details matter here. It really depends on the commitment scheme, but this is generally true for all the commitment schemes we use. And so it's linear in the weight. So
The weight of the witness.
The bit length of the witness. So let's say they're all 32-bit elements, then it's going to be proportional in 32. However, if then I need to do this product check, then additionally I need to commit to n 256-bit elements. So that part actually becomes the bottleneck in the SNARK computation. Committing to committing to sort of these partial products in the product check really becomes the bottleneck, and it's something that would get rid of, and sort of asymptotically, it's basically this lambda factor here that matters. Okay. So there are a couple other ways to do permutation checks, but they all, they have sort of various level of downsides. So, quarks use something, there's like a different formulation which doesn't use sums, but it uses something called logarithmic derivatives, essentially the logarithm, but the derivative of the statement still has the same issues. There's, it has still the same issues. Another variant is to
So is this like only when the field size is smaller than the secret?
which part?
So like you have this n
so there's kind of 2 fields. There's basically essentially the field or the size of the witness. My computation. So for example, what oftentimes happens, again, the devil here is in the detail, is that I'm executing my computation over some field or maybe even some ring. So for example, a 16-bit field or 32-bit field, because this mirrors what your computer does. But then for soundness, I need to use a larger extension of it. So the problem is that this commitment cost depends on the soundness field, not on the the actual witness field.
So if the actual witness field is also not there,
then this doesn't matter as much. But generally this is not what we see in the. But you're right. Yeah, when my computation is over 256-bit field anyway, because that is what I care about, this doesn't matter as much because I already am committing to it. Okay, there's another way, there's one way to get around this, which is to use a protocol called GKR. So essentially what I do is I implement, the product check using this. Have people heard of GKR? Okay. It's, like it's a relatively old proof protocol, but essentially the downside, so this gets rid of this additional commitment cost. The downside of it are that I have to do log n rounds of sum check to do this, which increases the verifier time and the proof size and the prover latency to log squared n. And it still has the same soundness issue. And GKR also, as we saw this morning, we talked about recursion. GKR is kind of expensive for recursion type thing. And recently there were some Fiat-Tremere attacks on the soundness of a sort of a more convoluted GKR circuit. This doesn't apply to the circuit that you would apply GKR here to, but it certainly is cautious, makes us cautious to apply Fiat-Tremere for deep GKR circuits. And here this would be a relatively deep GKR circuit. So just something, it's not a deal breaker, this works, but it would be nice to get rid of that. Okay. Any question? So the question is, can we do better? So our results are, well, I wouldn't be talking about this if I didn't have at least some results. So we have just 1 or 2 rounds of sum checks. We have better soundness. So it's polylog n over the size of the field instead of n over the size of the field. And our commitment cost is just having to commit to the original witness. And then you have to do, you have to open a polynomial commitment at that point. And we do, we have basically 2 solutions. This is where the n star, linear star comes in. We have one solution which has O of n field operations, and that can be instantiated with PCSs that essentially allow you to commit to sparse witnesses efficiently. So where the main commitment cost only depends on the number of non-zero elements. But that's not all PCSs. So we also have one that is, n times square root log n, and then some log factors in there, which works with any arbitrary PCS. Okay. And both of them have a log n verifier cost and a log n proof size, and it can essentially be used as plug and play for existing permutation checks, and as I highlighted before, it can be extended to lookups. Okay. So what is the multilinear? So to do that, we essentially said, okay, let's look at sort of this most basic formulation of the problem, and say the permutation is a map from 0,1 to the mu to 0,1 to the mu. What if we write it as a multilinear map? So what this means is we basically find mu polynomials, mu multilinear polynomials. So they're polynomials in mu variables, but linear in each variable. That is called sigma 1 of x up to sigma mu of x. So sigma 1 of x here implements the first bit of sigma, right? So if the first bit of sigma is 0, then sigma 1 of x is 0. If the first bit is 1, then it's so. And similarly, you can actually do the same thing for the inverse. So permutations are nice in that they have inverses. We can write the following relation, so xy is true if sigma of x is equal to y, and we can write the inverse. And then basically, we can, one other way to think about sigma I is to say that R sigma is going to be the intersection of all of these R sigma I. So if sigma of x is equal to y, then it means that sigma 1 of x is equal to y1. So it's equal to the first bit of y, sigma 2 of x is equal to y2, and so on. So yeah. So I also talk a little bit about, so if we, we can also write, so the other way to do this is to write this as an indicator function. So I have the indicator function of x and y, which is equal to 1 of x comma y is in R sigma, and 0 of x comma y is not in R sigma. And then it has this nice arithmetic form where 1 of sigma I of x comma yi, where I can just look at the product of these things. So you'll see we'll sort of more and more make this statement arithmetic. Okay, so why don't we, one thing that we could do is that I guess, so one thing that we could do is we could say that, why don't we prove this statement directly? Okay, so why don't we, this is the statement. There's something called a zero check, which says that, which essentially says that two polynomials or two multivariate polynomials are equal at all the points in the Boolean hypercube. So why don't I prove this directly? I already have this tool of zero checks. And the reason why I don't prove this directly is because essentially f of sigma of y, or f of g of sigma of y, or sigma inverse of y, are going to be quadratic in the size of. I want to go into all of the details, but essentially there's going to be a quadratic blow-up. So we need to do something slightly smarter. So what I can do is I can just write this in a different form. So I can say that instead of looking at f of sigma inverse of y, I look at f of x times sigma inverse of y of x, and is equal to g of y. And then I sum over all of the x values. So note that this part here, whoops, so this part here is going to be, if I fix a y, this is going to be zeros for almost all of the entries but one, right? This is like a one hot vector section. So it's only going to be one at one position. Namely, it's going to be 1 at the point where x is equal to sigma inverse of y, right? But so why is this better? It's just we can also flip the variables, and then I can use my permutation function again. But that's not really the the key point here is that, so why has this help? Well, what I've done now is I've essentially pulled out the sigma of the composition, right? There's no more composition of multilinear polynomials. And it turns out, again, I don't want to dive into all of the details here, but that these compositions of polynomials, they would be, or composition of multilinear polynomials would be essentially quadratic in size. And now that I've pulled it out, this is not quadratic in size anymore. So what is, but what degree is it? Well, this is going to be degree, so I can look at this. So, oops. Yeah. So this is degree mu and y on the right side. And then this is also actually, both of these are actually multilinear in y, right? Both the left side and the right side are going to be multilinear in y. I'm going to arithmetize it in a way, which means that, both of these, if I look at them as polynomials in y, they're multilinear polynomials in y, which essentially means that I can just evaluate them. So the left side and the right side are the same polynomial. So I can just test them at a random point. I can just sample a random point, alpha, and by the Schwarz-Zippel lemma, if two polynomials are equal everywhere, then they're going to be equal at a random. So now I've reduced this to this statement, right? So now I have kind of this sum check I've reduced it to the statement where I have the sum check, the sum here over f and 1, and this is really like what I need to prove. Okay, so before we do that, we have to actually like dive a little bit deeper into how exactly I'm going to arithmetize 1 sigma. And the first proposal of that came from HyperPlonk. So this is from an older paper. There was actually a section on this, and it said, okay, we want to arithmetize 1 sigma of x. Okay, so this is the key task. And I already told you that I can write 1 sigma of x of y as this product of the bitwise permutation. So 1 sigma I. Okay, so it turns out that so how do I write this product? Well, this product can be written in this particular form. I don't if you've studied these multilinear polynomials, this might look very familiar to you. If not, the only thing that we really care about is the degree of this polynomial in x. So what is the degree of this polynomial in x? Well, it turns out it's degree mu in every xi. Okay, and if we implement the sum check naively, this is going to give us a prover cost of n log squared n. But I skipped over detail here. I'm going to how do I prove the statement? I'm going to use the sum check. Are people here familiar with the sum check protocol?
Sorry, what is it here?
N is to the mu.
Oh, okay.
Because I saw it recently, and so I didn't write the permutation like a sigma, but I consider it as a vector having the permutation matrix as equal to a vector.
Yeah.
And this permutation matrix is like it is the SNARK matrix.
Mm-hmm.
So, and also this is a vector matrix product, and which can be also proven by the sum check protocol. So it has the same form, I guess.
Yeah. So so this would be basically saying that I'm going to arithmetize 1 sigma x of y as one big multilinear polynomial. The problem is that that polynomial has 2 mu variables.
Yeah.
So the size of the polynomial is quadratic.
Yeah, but I know there is like the pieces in Spartan. It has a sparse pieces.
Yes.
And I was wondering.
Can I answer why like this doesn't work, or what's the problem with it?
I guess the problem of it is that the memory checking of that sparse pieces, it has the bad sounds.
No, I think so. It works. So there are some PCS schemes.
Yeah.
So you generally in these polynomial commitments haven't talked about them, but they do matter. I'm going to describe this all as like evaluation of polynomials. But at the end of the protocol, the prover needs to convince the verifier that it correctly evaluated the polynomial. So we have, and so there's 2 main operations the prover does. One is committing to the polynomial, and then the other one is proving the evaluation of the polynomial. So the best PCS schemes, or like for sparseness, are only the committing is only linear in the sparseness. So this would work. The problem is that opening is square root in the size. It's linear in the sparseness plus lambda times square root in the size of the polynomial.
The prover, like the prover type.
Yes, the prover's cryptographic operations.
So its evaluation is that it's also a sum check protocol, and it adds the memory checking.
And you're saying if you're using Spark,
Yes.
but then you basically are at the same problem again.
Oh, what problem?
Like, well, memory checking requires a permutation algorithm.
Yeah. That's
Saying you want to.
the kind of a cycle.
Yes, yeah, that's yeah. So you could do that. There's also, okay, then I thought you were going into a different direction. I'm sorry. But yes, like they are kind of, there's the so-called Spark protocol, but at its heart, Spark uses another permutation argument. So you cannot, like, it's kind of circular to solve the evaluation using using memory checking, because then you need another permutation argument.
Yes, but I guess in their work they use the grand product to extension.
Exactly. So they have all the problems that I mentioned in the beginning. So they have bad soundness, and they have to commit to a large witness.
Yeah.
So this is the quark, for example, the quarks work. Yeah, that's sort of, yeah, this is basically what quarks does.
So can you show the work the soundness in the HyperPlonk?
So it's polylog.
No, I mean the in the HyperPlonk. Yeah. Okay, so in this permutation protocol, what's
the soundness is going to be, so the soundness of a sum check is essentially number of variables times the degree. So it would be mu squared over the size of the field. So it would be log squared n. So it would be good soundness. The soundness would be good. But the problem is, like, this is already, it's a decent solution. But the problem is that, now I've increased my prover time from, previously something that was dependent on n, and I don't have to commit to any additional elements, or at least long elements. But now I have this log squared n additional factor, which is not what I want. Does that make sense? Yeah. And I thought you were going in a different direction. There are polynomial commitment schemes, something like Dory, that directly allow you to commit to sparse polynomials. The problem is that if the polynomial is quadratic in size, they're not quite good enough, because their opening is lambda times square root of the size of the polynomial. The square root of quadratic is n, right? So you basically have like lambda times n commitment cost. So it's okay, but it's not quite good enough. So we're hoping for something better than. So this was basically the prior state of the art of sort of using. So our main idea is to reduce the degree of the arithmetization. Right. So we want to not use, right, like in HyperPlonk, we're doing a sum check of degree mu, and that's where a lot of the costs came in. So we want to reduce the degree of the arithmetization to something that is lower than mu. So the idea was, can we consider our sigma as an intersection of fewer than mu subrelations, and arithmetize each subrelation such that it's multilinear. And essentially what we can do is, we have two solutions. One is that we just look at, what if we just say, okay, one doesn't quite work. Like if we, directly arithmetize one sigma x, then it's quadratic in size. That doesn't quite work. Mu also doesn't quite work, because then the sum check complexity blows up. So what if we do 2? Okay, so for 2, then it's this one sum check, and essentially, the size of the statement, it's going to be a sparse sum check that's of size n to the 1.5, and that just turns out to be just good enough that it can be instantiated with some PCS schemes. Unfortunately, not all PCS schemes, but at least with some PCS schemes, that are, that are particularly nice for sparse polynomials. This works very well. This is essentially, you can look at this as an equivalent to result to something that was published in, called Shout in the same year. And then the second result, sort of the main result, says that we're going to look at, not log n, subrelations, but we're going to look at square root log n subrelations, and essentially have two sum checks, and then through some tricks and so on, we'll get our prover cost down to n times square root logging. But this one works with any PCS. It doesn't require any sparse. Okay. Yeah.
Sorry, I kind of missed this, but how does this compare to Shout?
One is you can look at the result as essentially the same. So the first thing, you can essentially look at the same result as Shout.
So okay.
It's essentially the same.
What are the differences?
They look at it as a lookup argument. We look at it as a permutation argument. But as I said in the beginning, those things are highly related.
Yeah.
So yeah, there's some differences where we specifically treat things as permutation argument and make them slightly more efficient. But yeah, for all intents and purposes, I would claim it's essentially the permutation variant of what Shout is for lookup arguments. But both of them only work with some PCS schemes. So in particular, they don't really work with hash-based PCS schemes. Versus the second result works with hash-based PCS schemes, which tend to be the things that people care about slightly more in practice.
So for those pieces, it commits to a polynomial which has either until the 1.5, but it has also linear time prover and all time prover.
Yeah.
Including the evaluation.
Yeah. Well, because the square root of 1 to the 0 n to the 1.5 is n to the 0.75. So you suddenly, like, the opening is suddenly efficient. So yeah, but there's only a few, and they're all group based and PCS schemes that satisfy those requirements. Versus the second one is satisfied by much more polynomial commutes. But yeah, certainly an open question is, can we design even better polynomial commute schemes? So I'll, I don't want to go into, all of these details, but I'm gonna, at least try to give you some of the highlights. So what we're going to do is, I'm basically going to group. Right now it's mu subrelations, and then I'm going to group them basically in buckets of size mu over L, and then I only have sub L relations. So so now it's just the product of L things, and now the degree of my sum check is just L. It's not mu anymore, it's L. Okay. So and then in the second step, I'm especially in sort of our main result, we're going to prove that R1 can be written again as the product, or each Ri can be written again as the product of mu over L relations. And this is where so I'm going to set in the optimal setting, I'm going to set L to be square root of mu, which is the same as square root of log n. And then essentially these two problems become roughly the same. So yeah, and then I prove the correctness. So I do this essentially as a two-step protocol. You can think of it as a very low depth GKR circuit. So for L equals 2, I'll just give this as an example, and then skip ahead a bit. So there, basically, how can I, like, thinking back to our original problem, what can I think of as 1L and 1R? Well, basically 1L says that the first half of the bits of Y agree with the permutation of X. And 1R says that the second half of the bits agree with the permutation of X. And then so if I look at this in detail, right, I can think of this as, this one does not actually completely ignores the second half of the bits of Y, and this one ignores the first half of the bits of Y. So I can really look at these as multilinear functions in x and yl and x and yr. So how many variables do they have? Well, x is mu variables and yl is mu over half. And same here. So they have 1.5 mu. Oops. Did I write this somewhere? This is 1.5 mu. 1.5 mu variables. And the size of a multilinear with k variables is 2 to the k. So this is 2 to the 1.5 mu. 2 to the mu is n, so it's n to the 1.5 in size. However, it's very sparse, right? It only has n non-zero or n bits. So the prover basically it sends oracles to HL or HR, or in our case, these things are actually preprocessed, so they're committed beforehand, and then verifier picks a random alpha, and then we prove the sum check. This reduces to 3 claims, right? Once I run the sum check, I reduce to 3 claims about f of b beta HL of this and this, and I guess I have the 4th claim on G here. Sometimes f and g are the same, so this is one query. And so the verifier queries these oracles and checks these claims. Or if I implement this with a polynomial commitment, then the prover will open the polynomial commitment at these points and prove that they were evaluated correctly. So in total, this is a sum check of a virtual polynomial 3. It has a PIP with prover complexity of n field operations. So yeah, this requires a PCS, which has cost and sparsity. Yeah, let me just jump ahead. So in, kind of, as I said before, and, I don't want to like go into the details, but, we need to do for the general result, we need to do a lot more tricks. But essentially, we have these 2 layers of bucketing, breaking things into L problems, and then, doing that again. And this is, our total, because the degree is basically going to be square root of mu, our total prover cost is going to be proportional to n times square root log n. And we can, to do this, one main thing that we take advantage of is that, so if you did this naively, this wouldn't, this result doesn't jump out. One main thing that we have to take advantage of is that if we look at, if we look at one, these polynomials, these extensions of one, if we look at the image space, it's all just zeros and ones, right? So the image space is just zeros and ones. So I'm running a sum check over a product of polynomials that are only zeros and ones, right? It's really, really constrained image space. So for example, I can actually, in sum check, I can, for example, list all of the lines that go through 0 and 1. There's 4 of them, right? One goes from 0 to 1, the other one goes from 1 to 0, the other one, third one 0 to 0, and the 4th one from 1 to 1. And it turns out that I can take advantage of this in the first couple rounds of sum check. I can literally enumerate all the possible functions or values that the sum check can take up, and with that I can speed up my computation. Again, if you want to know more, I encourage you to read the paper. We then extend it to lookups. There, one thing that it makes it a little bit more complicated is that previously we took advantage of the fact that permutation has an inverse. This is not going to be the case anymore, but we can use something called the pseudo inverse. So basically all the things that map to X and still get a similar result. Okay, so all of this together, what, we can get to questions. So what did we do? We have, a permutation check, or this, yeah, well, what did we do is we designed a permutation check that has a small soundness error, which makes it better to, for example, apply over small fields. which if you're willing to use some particular polynomial commitment schemes, has linear prover time. If not, it has this like weird square roots log n term, or maybe hiding some log factors in there even. So there's some obvious open future questions that certainly I will be looking at, but I certainly encourage the community to look at. The obvious one is, can we get a permutation check with the prover performing O of n field operation that works with any PCS? Ideally small constants, ideally preserving the soundness, verifier costs and process. The second question, that sort of comes interesting is like, if I want to prove things over, let's say, really, really small fields. Right now, our soundness error is polylog n over the size of the field. Can I get a constant size soundness error? So we probably have to change, some parts of the subject protocol there. But yeah, that's another interesting question. And then the third one that isn't on here is like to see. I mean, I believe these things are practical, but like we haven't implemented them, and they're like one other thing, one other caveat that I'll say is that we're counting only field operations. So for example, you might wonder, well, like in a permutation, don't I need to sort or something like this? Well, we're not counting any of that. So we're only counting pure field operations, which tend to be the most expensive cost. But it's, it would be good to implement it and see whether this actually holds true, whether we're missing something, sort of some non-arithmetic operations, and yeah, whether this is actually practically efficient.
So,
Yes.
so the listener don't have the implementation.
It's fine, it's not a implementation. Yeah, no, it's certainly missing. But yeah, thank you very much. Any more questions? Are there any questions?
Don has a question.
Don, go ahead.
Oh, no, he's there.
No, I was clapping, but that's okay. It's very nice. I can make one up on the fly though. So the square root n is an interesting limit there. This is wonderful. I think it's great. I love these things where polynomials take the day. But the square root of n, do you think there's improvement on that, or is it? Do you then get more and more layers going on to try to improve to like? Could you get better than the square root of n kind of cost in there?
Yeah, it's really like, I mean, the square root of n, or the square root of, you mean in our protocol, right?
Yeah, I think you have two layers. You bound two portions, and then you're sort of trading that off.
Yeah,
and it's sort of natural in that, but I don't know if there's like a 3 or 4 different breakdown thing that you could get to n to the 1/4 or something like that at a different
right.
cost.
I mean, that's a very natural question. Like it's not obvious at all. Partially because basically, even to achieve this square root mu result, we need to take advantage really of this image space being so small. So it's not just like you just set it up in the structure and it falls out immediately. We really need to take advantage of the small image space, and that one, it actually like that one blows up, very, very quickly. It's like 2 to the 2 to the k, where k is the number of rounds that you're able to do. So that's really where where maybe some of the bottlenecks come from. But I mean, I would be surprised if this is or I would hope that this, this paper is not the end of the line. But that we, like, yeah. I mean, it's hard to predict the future, but I really hope that we can do better than like a weird square root log n factor. It just doesn't feel natural.
Yeah, no, sometimes it is, and sometimes it's just it's like a Grover's algorithm or something where it's just that you're kind of stuck with it, sort of thing, and sometimes it's not. And there's if you're costing an extra 2 to the 2 to the something as your constant in the O notation as you trade off parameters a little bit, that's horrifying as well if you try to implement something. So it's kind of good to have that intuition. So thanks. Yeah, it's awesome.
Any other questions? enough talks for today.
So do you have a like a lower bound for this problem?
And
So ON like field operation?
yeah, I mean, it seems kind of natural that, I mean, like, do I have an actual law about, no, it seems natural that you would have to do at least n operators to prove
So
it.
there's like no iter.
No, I mean, no, well, we do actually, so I skipped over this relatively quickly. We can actually achieve O of n by running, so there is, yeah, with the sparse PCS, we can achieve O of n, and also, I can, if I apply GKR to essentially the first, you know, this thing, then I do actually get O of n prover time. The problem is, and I don't have to commit to anything. The problem is that it has soundness error and it has band verifier time. So it's really like we're looking. We can achieve everything, but not. But we don't have the dominant, you know, the thing.
For linear start at the beginning.
Well, because it's one protocol is linear, and then the other one has like square log n. I mean, square log n, if you think about it, is like 3 or 4, right? Like it's really not, you know. Okay, maybe not 3 or 4, but like yeah, it's almost at the point where, you know, one thing that I would actually be interested in is really figuring out the constants, because when you're talking about square log n, right, constants tend to matter almost more than those factors, right? If you have a hidden constant of 10 somewhere, it's certainly bigger than square log n. Or, yeah.
If I want to achieve the ON over time, can does the pieces contain the breakdown spec again?
Great question. So there are some hash-based PCS schemes which have a fast opening time. We just submitted something to ePrint, which also has this property. The problem is, so what you do in a hash-based PCS is that you first encode your witness. What we know, if it's a good linear code with good distance, it's very easy to prove that even if your witness is sparse or your input is sparse, the code, like the cannot be sparse. It cannot be sparse, right? Otherwise, it cannot have good distance. Like distance is literally related in linear code to the number of low weight code words. So yeah, so what, you know, so basically the commitment operation is not linear in the sparses in breakdown. Like the opening is fast, but the commitment operation. One thing that you might say is that the commitment is done during pre-processing in, you know, especially in the SNARK application. It might still be interesting because the commitment is done during pre-processing. And maybe during pre-processing, you have more time. Maybe n to the 1.5 or whatever is fine during pre-processing. But now it becomes a really strange trade-off. But yeah, basically, I think my general statement that I think is true is that none of the hash-based PCS schemes can ever be friendly for sparseness. Like maybe lattice-based ones are interesting to look at if you care about the post-quantum. Awesome. Anything else? Okay.
Thanks, Benedikt.
Thank you. Yes.